Hello, everyone. You've got Sidhanth here. And today I'm going to talk about testing thresholds in random geometric graphs. And this is based on joint work with my wonderful collaborators, Siqi, Tselil, Schramm, and Elizabeth Yang. So let's first talk about the model of random geometric graphs. So you have n vectors, which we're going to denote v1, v2, up to vn, which are sampled independently and uniformly at random from the surface of the d-dimensional unit sphere. And each vector is identified with a vertex in the random graph that we're drawing. And we connect vertices x and y with an edge if they're sufficiently close, where sufficiently close is articulated by the inner product vx dot vy exceeding tau of p. And the threshold tau of p is chosen so that an edge exists between x and y with probability p. So here you see how xy is an edge and xz is also an edge. Just to give you a sense of like how large tau of p is, it's going to be approximately square root of log 1 op over d. So when d is large, the threshold is actually really small. It goes to 0. And we're going to denote this random graph model with the notation geo sub d and p. So now let's get into the motivations for studying this new model of random geometric graphs. So actually the key motivating property that's present in random geometric graphs, but not in the more standard Erdős-Renyi graphs is the following. So if I tell you that two vertices B and C are both connected to a vertex A, then actually the probability that there is an edge between B and C goes up. In particular, it's greater than P. So this key motivating property makes it so random geometric graphs might approximate real-world networks better. In particular, if you take a social network, two of your friends are actually more likely to know each other than two random people on the internet. So because of this property, it might be a somewhat more faithful test bed for algorithms on graphs for various questions that we might care about, such as clustering and partitioning. And another motivation to study this other model of random geometric graphs is the probabilistic method. So actually studying Erdős-Renyi graphs has given us some really fruitful results in the past, where we know the best constructions of Ramsey graphs, namely graphs with no large Cleeks independent sets, actually come from random graphs. Also, the easiest way to convince yourself that like an expander graph exists is to prove that a random d-regular graph is an expander. So now we have a new random graph model, and maybe this might have applications to the probabilistic method. For instance, it might potentially be a way to construct high-dimensional expanders, where maybe you should think of high-dimensional expanders as being expanders with expanding neighborhoods. I guess that's what a two-dimensional expander is. Okay, but now we've defined this new model of random graphs. We want to study its properties. But question number 0, the first question that we would like to answer about random geometric graphs is the following. Is this graph actually any different from a completely random Erdős-Renyi graph? So in particular, we got these vectors. The vectors gave us a graph. Okay, now we've forgotten about the vectors. We only have a graph. Is this graph faithful to its underlying geometry? Does it look any different from an Erdős-Renyi NP graph, which we're going to call GNP? So concretely, the Erdős-Renyi model is the one where for every pair of vertices x and y, you place an edge between them with probability p. And we would like to know for what dimension are the two models, the Erdős-Renyi model and the random geometric graph model, the same? And when are these two genuinely different models of random graphs? So one thing to note is as the dimension goes to infinity, this threshold tau of p for connecting two vertices goes down. And this sort of encourages edges to be more and more independent. So the behavior we expect is when you have a really low dimensional geometric graph, it looks very different from an Erdős-Renyi graph. And as you increase the dimension, it looks more and more like an Erdős-Renyi graph. And we would like to get a more fine-grained understanding of where this threshold for dimension lies. And one more piece of notation before we move on the talk is you're going to use GG of V1 to Vn to denote the proximity graph of given vectors V1 to Vn, namely the geometric graph that they produce. Okay, so this question of distinguishing additionally graphs from non-geometric graphs was actually studied a few years ago by Bubeck, Ding, Eldon, and Rocks. And they proved that when the dimension is much smaller than a particular threshold, and the threshold is n cubed times a binary entropy function of p cube, which here we call h of p cube. Actually, when d is smaller than the threshold, these two models are distinguishable via certain small subgraph counts. These subgraph counts are some linear combination of the number of triangles, the number of wedges, and the number of edges in the graph. And actually, they also prove that these two graph models are indistinguishable when the dimension is a lot larger than n cubed. Now, if p is like a constant, say half, then the result is actually tight because the entropy function of p is a constant. But you see there is a gap that takes place when p is decreasing. So in particular for sparse graphs, the picture that they draw has a pretty big gap. And in an effort to close this gap, Bren, Bressler, and Nagaraj studied this question. And they showed indistinguishability for somewhat improved parameters. These were better parameters, but they still didn't quite close the gap. So here, just to make the results more easy to visualize, we've expressed this in like a phase diagram. And in this phase diagram, the green region is when Bubeck, Ding, and Rocks proved that the two models are distinguishable. And in the red region, is the indistinguishability that we know so far. And let's now zoom in on the regime that we're going to be interested in this talk. We're going to be interested in the very sparse regime, namely where the average degree is a constant. So when the average degree is a constant, this p parameter is theta of 1 over n. And note that we know that these two models are distinguishable when d is a lot smaller than log cube n. But the current phase diagram tells us indistinguishability only above n to the 1.5. So it's a pretty big, actually, in fact, an almost exponential gap between the distinguishability and indistinguishability and the sparse models. And the main result is closing this gap in the sparse regime, namely where we show that when d is at least some polylog n, in this case log to the 36n, these two models are indistinguishable. We also get some sort of improved indistinguishability for the remaining p. So a couple of remarks are in order. In the regime that we're mostly interested in, our results are actually tied up to only polylogarithmic and n factors. Whereas I guess for the remaining regime, it's lose by a fairly big, like 1 over entropy function of p factor. So yeah, I guess an interesting question is to try to get a nearly tight result even for the remaining regime. And in this talk, we're mostly going to focus on the sparse regime. So now, what exactly does it mean to prove that two distinct distributions are statistically indistinguishable? It means we want to prove that the total variation distance between an addition graph and a random geometric graph is little of 1, is going to 0 as n goes to infinity. Okay, so to do this, we're actually going to break down a question into a simpler problem. We're going to reduce this to studying only neighborhood distributions. So you can think of sampling like either of these graphs vertex by vertex, and every time a new vertex arrives, it samples its neighborhood according to some distribution, either the additionary neighborhood distribution or the random geometric graph neighborhood distribution, and then it connects to its neighborhood. And actually, by like a rather standard argument, a standard in the context of information theory, which just for those who might be curious, it's like a combination of principles of inequality and the fact that relative entropy tensorizes. It actually suffices to prove that for most sets, the ratio of connecting to the set the ratio of the probability of connecting the set in the random geometric model against the Erdős-Renyi model is very close to 1. And in particular is about 1 plus minus 1 over square root n close to 1. So now I've told you this ratio. So now we should actually get into what the numerator and denominator are. So let's look at the denominator. The denominator, what is the probability that S is chosen as a neighborhood for a new vertex in the random geometric graph model? In this model, you choose each vertex independently with probability P. So a given set S is chosen in your neighborhood with probability P to the power cardinality of S times 1 minus P to the power T minus the cardinality of S. And okay, that was a simple enough expression. The thing that we're actually going to spend the rest of the talk on is how do we get a handle on the numerator of this expression, the probability that you connect to S within the random geometric graph model. So, okay, let's understand. So you first do the following. You have this graph G at most T that has been sampled so far. And what you do is the first step is you first look at some random assignment of vectors on the sphere, which actually generate G at most T as its graph. And then around each of these vectors, you drop down a spherical cap. Now, once you've dropped down a spherical cap around each of these vectors, you've actually partitioned your sphere into these regions that we call splinters. So what is a splinter of a set S, where you think of S as being a subset of 1 through T? You take every vector that is in the set, draw a cap around each of these vectors, and look at the intersection of all these caps. And then intersect this with the intersection of the complement caps of the vectors that are not in your set S. So as you can see, these different colors denote like different splinters. Okay, and then now you choose a random vector for the new vertex that arrived, Vt plus 1. And you choose the S whose splinter that the random vector falls into. And in particular, under this process, S is chosen as your neighborhood with probability equal to area of the splinter of S. Actually, we also randomize over the vectors. So the probability of choosing S as your neighborhood is the expected area of a splinter of S over this distribution of vectors V1 through Vp conditioned on producing G at most T. So, okay, one thing that I want to get across conceptually is actually even the definition of a splinter. So we're going to go over an example of what a splinter is. So in this example, just think of T as being equal to 3. So there's only 3 vertices, 1, 2, 3. And the set S that we're going to be interested in is the set 1, 2. Okay, so now let's look at what the splinter of 1, 2 is. The splinter of 1, 2 is the intersection of the cap around V1 intersected with the cap around V2 intersected with the complement cap around V3. So V1 was a cap, V2 looks like this convex length shape, and V3 actually looks like this convex length shape chomped out because the intersected complement cap. Okay, so hopefully this example makes what a splinter is somewhat more clear. So now let's go back. Okay, so now I'm telling you that I want to actually get a good estimate, not only of the area of a splinter around S, but on the expected area. And this expectation seems to be over a somewhat crazy distribution. So I guess I'll have to sort of tell you how one gets a handle on this distribution, how one can see this distribution as being somewhat tame. So, okay, the goal now is to understand the posterior distribution on the vectors V1 through Vt, conditioned on producing a graph G at most T. And actually, the key property of interest to us is going to be to prove that for a given set S, so only a small subset of these vectors, Vi for I and S, they're actually all approximately uniform, and they're also all approximately independent of each other. And in the rest of the talk, I'm going to go over like how one actually tries to establish this. So, okay, let's restate our goal. Given V1 through Vt, our goal is to understand Vi for I not in the set S. And we can actually view this as a constraint satisfaction problem that is given to us by the graph G at most T. In particular, for every edge, ij, we have the constraint that the inner product Vi dot Vj exceeds tau of P. And for every non-edge, which we've marked as one of these cross edges, Vi dot Vj actually must be less than tau of P. And now the posterior distribution is the uniform distribution on solutions to this constraint satisfaction problem that we just defined. So, okay, now we would like to prove that when we look at the uniform distribution on this space of satisfying assignments of the CSP, for the marginals on a small set S are approximately independent and uniform. Okay, so now one thing about S is actually typically going to be a constant size set, or maybe at most a logarithmic size set with high probability. So if you take a typical set S in your graph, because of the sparsity of this graph G at most T, it's going to be locally tree-like. Namely, if I draw small balls around S, actually around all the vertices in S, they're actually all going to be disjoint balls, and they're going to be pretty far away from each other. So now the strategy is going to be to prove that if I fix vectors in the purple part of this graph, namely the bulk, the stuff that's outside all of these balls, then even after I fix those vectors, the resulting conditional distribution on Vi for I and S is still approximately independent and uniform. Now, actually, by sweeping some small details under the rug, we can actually treat the CSP instance that we get after fixing the vectors in the bulk as being a CSP instance on a bunch of disjoint trees. But since you have a CSP instance on a bunch of disjoint trees, you get independence of free because the disjoint pieces don't correlate with each other in any way. Or rather, the distribution of vectors on the disjoint pieces don't correlate with each other in any way. And then the goal is going to be to show some sort of approximate uniformity for each Vi. We've already shown independence, now we care about showing approximate uniformity. Okay, so now let's zoom into one of the trees. What happened when we fixed vectors in the bulk? Well, the vector assignment to the leaves of this tree got fixed, but the remaining vertices don't have fixed vector assignment. So we want to show that for almost any assignment that the leaves could have received, the root, which is colored red, conditioned on the vector assignment of the leaves, is approximately uniform. And the way we get a handle on this is actually using the belief propagation algorithm. So I'm not going to get into the details of what belief propagation is or how we use it to analyze the posterior distribution on the root. But maybe I will talk about like a nice, clean, self-contained math question that came about in this analysis. So here's a relevant question to the analysis of belief propagation. Let's say you have an arbitrary set L on the surface of the unit sphere. So I can look kind of crazy, like this yellow set depicted in this diagram. And W is a uniform vector on the surface of the unit sphere. Now we draw a cap of measure P around W. And now we want to know what the concentration properties of the area of L intersect cap of W is. And we actually do need to show some pretty good concentration properties for this quantity. So first of all, the expected value of this area is simply P times the area of the yellow set L. And just to get intuition for what kind of concentration I will tell you about, let's consider two extremes. One extreme is when the set L is a point mass. When L is a point mass, actually, if I put down a random cap, I either completely contain L, in which case the amount of picked up is the area of L with probability P, or I don't contain L at all, in which case I actually pick up 0 with probability 1 minus P. So this is actually some really bad, this is like terrible concentration. But now let's consider another extreme when L is a full sphere. Now, no matter where I place my cap, I'm actually always going to have area P times area of L. So there's a perfect concentration. There's no fluctuation at all. So the takeaway from looking at these two extremes is that somehow whatever theorem we prove needs to depend on the area of L. And this motivates the next statement. The theorem is the area of L intersect cap W is within a 1 plus minus small fluctuation times P times area of L with high probability, where the order of magnitude of this fluctuation is square root of the log of 1 over area L. So you see how when you increase area of L, it gets better, and when you decrease it gets worse, divided by D. So when you increase the dimension, it gets better. When you decrease the dimension, it gets worse. So this concentration is like a somewhat high dimensional phenomena. Thank you all for watching, and feel free to send me or any of my co-authors an email if you have any questions or thoughts or feedback. Thank you very much.